Before I forget, I did want to mention that your next Canvas quiz is available, or will be, as soon as you leave lecture tonight, or this afternoon. So it's on aromatic nomenclature. So that was the homework that you submitted last time. So I graded that and returned it on Canvas. So what I would recommend you do is just have a look at those results, see if you missed anything, see where you missed things, and then whenever you're comfortable, you can go onto Canvas and take the quiz. So if you go under the quiz section, you'll see that by the time you leave this afternoon, there will be one available, and it's called simply aromatic nomenclature. And it will be much like those problems you had on the homework, okay? So just sometime between this afternoon and our next meeting, Monday 11:30, that's when it will close, okay? All right, so I had a thought. I don't know if this would be beneficial or not, but normally I don't generally record lectures because I'm usually at the board. But in this current situation with the lighting and everything as it is, I could try logging into Zoom and recording the lectures that way, if that would be something useful. I've never tried it on the iPad. Generally, whenever I do the Zoom lectures, I have my computer open and then kind of AirPlay my iPad to the computer. And that's how I do it. But unfortunately, for some reason, in this room, the AirPlay does not work. So I don't know if the Wi-Fi is not good enough or what the problem is. I'm no tech guru. I just know that it doesn't work. So what I can try doing is zooming on my iPad and then recording it that way. I don't know how good it will work, but we can give it a shot if that is something that people would be interested in. So. All right, so let me go ahead and see if I can do that.
That's kind of what Professor Casale did last semester.
Oh, was it?
She would sit up in front with the camera and the iPad.
Okay.
Record it.
I'm gonna go ahead and record today just to make sure.
Yeah, I wouldn't do that myself. Okay, so what do I want to do? Record to cloud. Share screen. So, I think we should be in business now. So if this ends up working, then I will start posting the lectures onto the Canvas site, and that way you can access them if and when you want to, okay? All right, so let's go ahead and get started. Last time we met, we were talking about the reactions of benzene compounds, and we had gotten through all of those electrophilic aromatic substitution mechanisms, right? The halogenation, the nitration, the sulfonation, all of the Friedel-Crafts variants. And then we had begun talking about the kind of random benzene reactions. So I think we talked about side chain oxidation, we talked about hydrogenation of the benzene ring itself, and I think where we ended, we were talking a little bit about the benzylic bromination. So this is very much like that allylic bromination that you learned last semester, right? Instead of a double bond, an alkene, we're going to be dealing with a benzene ring. So you can take these benzene compounds and under a couple of different conditions, you can simply just use bromine and light, or like you did with allylic bromination, you could use NBS.
Do you mind if we pull the screen down?
Oh, yeah.
Thank you.
So under either of these conditions, you will get brominations at that benzylic position, which is just adjacent to the benzene ring. I think we talked last time, when we were doing allylic bromination, NBS was really the preferred method, because if you were to try to use ER2 and light on an allylic position, there was a chance you could add bromine across the double bond, and just do a simple, make a simple dibromo alkane. The reaction conditions had to be controlled very tightly for the concentration of bromine in solution in order to get exclusively allylic bromination. And so people don't like to do that, it's a lot of work, so usually when you're doing allylic, they just use NBS. You don't have to worry about adding bromine across a double bond in benzene for reasons we talked about, right? If you were to add bromine across any of those double bonds in the benzene ring system, you would end up breaking the aromaticity, and that's a very unfavorable thing to do. So it doesn't matter how you do the bromination with these benzylic brominations, you're always going to get exclusive bromination at the benzylic position. All right? Now, why would you want to do this? It turns out that this is a very, very useful reaction, and you'll probably be using it quite a bit in your synthesis. Because once you have a benzylic bromide, there's a lot of directions you can go. I could take the benzylic bromide, and adding magnesium, I can do Grignard chemistry. I could take the benzylic bromide and adding nucleophile, I can do substitution reactions. I can take the benzylic bromide, I can add base, and this one you might want to use a bulky base just to make sure you don't get substitution. But anyway, strong base, and you can get eliminations. Well, once you get that elimination, you get that alkene, then you can do all of those different alkene reactions. So these benzylic bromides are very diverse. They give you a lot of options for further functionalization. Okay? Any questions on this one? Okay, then let's move on to the last of these kind of random benzene reactions. And this is a named reaction. This last one is named for the Australian chemist Arthur Birch. And it's called the Birch reduction. So the Birch reduction is a really interesting reaction, both in terms of how it's done, and it's also a fun reaction to do. It takes a benzene ring, and you're going to use a few kind of strange reagents. And it uses an alkali metal, so either sodium or lithium commonly. It uses ammonia in a liquid form, and then some sort of a protic solvent. And what this does is it will convert the benzene into a 1,4-diene. So it makes something like that. So before we get into the why this would be useful to do, I think we need to talk a little bit about some of these conditions. So first of all, you'll note that the ammonia in this reaction is used as a liquid. Well, that's a little bit weird because ammonia is a gas at room temperature. And so in order to accomplish this, you've really got to get everything very, very cold. So the way this is typically done in a practical sense is you would get a round bottom flask, you would add your ethanol to it, you would add your whatever you're trying to reduce, the benzene compound, and then you would have a lot of organic chemistry labs have an ammonia tank, so it's just a gas tank full of ammonia gas, and then you would connect a line to the round bottom flask. And this has to be, as I said, very, very cold because in order to have ammonia as a liquid, you've got to condense it, right? So you typically have some sort of a dry ice acetone or dry ice isopropanol bath, which is around negative 78 degrees Celsius, so very, very cold. So you have to do this a bit carefully. So you would turn the gas on. It'll begin to flow into the round bottom flask, and when it meets that very, very cold condition, it begins to condense and gives you that liquid ammonia. And then what you'll do, once you've got a sufficient quantity of the liquid ammonia in the flask, is you'll chop up pieces of the alkali metal and then chuck it in. And as soon as you do, it's really quite striking. Everything turns this beautiful, brilliant blue color as the alkali metal hits the ammonia. And the reaction's really quite simple after that. You let it stir for 30 minutes or so. At the end of that time, you take it out of the cold bath, take the top off in the hood, because you don't want to be breathing in a bunch of ammonia gas. But you let the ammonia evaporate, and then you're left with your compound dissolved in ethanol. So it's a very nice reaction. You generally get very high yields of the 1,4-diene. So that kind of begs the question, who cares? What's so useful about a 1,4-diene? Well, nothing really. But it allows you to do something that's very difficult to do by other means, and that is break the aromaticity of the benzene. You know, we talked about this a little bit last time, that it's possible to hydrogenate the benzene, but it's not easy, right? If you're going to use palladium, you've got to have the 1,000 psi of pressure and specialized glassware and all the rest. You can do it with more exotic catalysts, but who wants to spend $27,000 an ounce on rhodium? You know, so it's not exactly the easiest thing to do if you want to try to hydrogenate the benzene ring to cyclohexane. But this is a very convenient way of kind of substituting for that, because once you break the aromaticity of the ring, well, these are just regular old double bonds. Very easy to hydrogenate out. Hydrogen gas, palladium, atmospheric pressure, and poof, they're gone. So the Birch reduction using very inexpensive reagents, sodium metal, ammonia gas, is able to break the aromaticity of the ring, and then if you want cyclohexane derivative, then you simply just do regular old hydrogenation and get it. Okay? So that's kind of the utility of the Birch reduction. And this is really useful synthetically. You know, if you think about trying to make cyclohexane rings, which people want to do all the time because they're found extensively in nature, it's hard to functionalize cyclohexane rings. You know, if you think about what are the reactions you know to put things on a cyclohexane? Probably just one, right? Photobromination. So there's not a lot of options there to try to put groups on the cyclohexane. But I know a lot of reactions that I could use to functionalize benzene. We spent the last lecture and a half talking about them all, right? So you can go through and put X, Y, Z all over the benzene ring, do a Birch reduction, and depending on what groups you have on, you're going to get some form of a 1,4-diene. And then just hydrogenate them out. So it provides a pretty nice way of making these highly functionalized cyclohexane rings. Okay. Any questions about this so far? Okay, I think it's worth going through the mechanism of this reaction because it's probably not immediately apparent how this happens. But the point of adding the, I think I'm just going to redraw it. The point of adding the alkali metal is if you think about those alkali metals, they have a single valence electron, and they are not held particularly tightly. Right? Alkali metals very easily give up their valence electron. Or said another way, they have a very low ionization energy. And so when you put this in solution with the ammonia, what ends up happening is the sodium metal is going to give up its valence electron essentially to the ammonia. And this is kind of a weird thing, but what ends up happening is you end up with that valence electron that ends up getting solvated by the ammonia. You'll hear it sometimes referred to as a caged electron. Right? If you think about the ammonia, right, that those bonds are polarized. The nitrogen is delta negative, all the hydrogens are delta positive, and so the ammonia kind of forms a cage around the electron with all of those delta pluses pointed at the electron, and it's almost like an ion dipole interaction. And so what ends up happening here is the electron, the single electron, will add into the pi system of the benzene. So this is a one electron transfer, so I want to make sure I use my correct arrow. I'm not going to use the double-headed arrow because that's for an electron pair. Here I'm going to use my fishhook arrow. And that's going to cause these electrons in the ring to shift. So what that results in is an intermediate that looks like this, or what we term the radical anion. And then the point of having the protic solvent, the ethanol solvent, is that it gives a proton source to protonate the ring. So we end up making, after protonation, this radical. And then it happens again. A second electron adds. Making the electron pair. And then that protonates from the protic solvent as well. Ultimately giving you that 1,4-diene. Okay, so the Birch reduction is fine. You know, that's kind of the long and the short of it if you have an unsubstituted benzene ring. However, the story gets a little bit more interesting when you start trying to do it with a substituted ring. So what I mean by that is, do you see how if we had, I'm just going to give a hypothetical substituent on the ring. You see how if we were to do the Birch reduction here, we could get two different products, two different isomers, two different 1,4-dienes. I could get that. Or I could get that. You see how those would be different products? So what do we think? You just get a 50-50 mixture of both? I'll give you a hint. Generally, if you're getting a 50-50 mixture or a 30-30-30 mixture, some even distribution of products, it's usually a garbage reaction and you wouldn't be talking about it. So No, we don't see a 50-50 mixture of these products. One of them is generally predominant, and it depends on what type of substituent you have on the ring. So we'll talk a lot more about this in lab today, but we talked a little bit about it so far. We've talked about the difference between electron donor groups and electron withdrawing groups. We talked about that in the context of Diels-Alder chemistry. That is really going to determine which of these two isomers forms, whether the substituent group is a donor group or whether the substituent is a withdrawing group. So let's look at it in both ways. So if I had an electron donor group on the ring, let's just do anisole. And I were to do the Birch reduction here, it really depends on where the electron adds to. All right, I really have two choices here. So the electron can add either to that carbon, or it can add to that carbon. And the distinction here is that it leads to two different radical anions, and thus two different products. So let's imagine the blue one first. If I added to the carbon opposite the electron donating group, I'm going to end up with a radical anion that looks like this. And it would ultimately lead to a product that looked like this. Alternatively, if we added to that other carbon, the one kind of meta to the donor group, we would end up with a radical anion that looks like this. And a product that looked like does that make sense? Can everybody see the difference there? Depending on, now that we've made the ring unsymmetric by putting a substituent there, depending on where the electron adds, it's going to lead to different radical anions and thus different products. One of those radical anions is better than the other. Anybody have an idea which one would be better? Yeah.
Well, if the OCH3 is a withdrawing group.
No, donor.
No, it's a donor group. Then it's gonna work better on this one, isn't it?
Yeah, I would agree. All you have to do is look at the electron density in the radical anion in blue. You've got all of that, the lone pair here, right next to all of the lone pairs of the oxygen. That's a whole lot of electron density right next to each other. I mean, this isn't a great intermediate, because you're still talking about a negatively charged intermediate with an electron donor group. So that's still a lot of electron density, but at least it avoids having all of that negative charge right next door to all of the lone pair density. So in a case like this with an electron donor group, it is much more favorable to make this type of a radical anion leading to this type of a product. So in a case with the electron donor groups, we tend to see the major product like that. Now we can go through the same exercise and kind of illustrate why an electron withdrawing group would be different. So let's just say instead of anisole, let's do the same exercise with let's say acetophenone. So we're going to do the Birch reduction. And again, just like before, because we've made the ring unsymmetric by putting one substituent on it, it can add there, or it can add there. And again, that's going to lead to two different products. If it adds para, we get that kind of radical anion leading to this type of product. If it adds meta, we get that kind of radical anion. Leading to that kind of product. Now in this case, it's actually more favorable to have the negative charge right aligned with the strong electron withdrawing group. In fact, if you think about it, I can draw another resonance form of this, where I pull that lone pair into the carbonyl. So that has a much more stabilizing effect than just having it kind of randomly in the ring. So in this case, with the electron withdrawing groups, it's actually more favorable to have this style radical anion giving this type of a product. All right. Any questions on the Birch reduction here? All right. Then if not, we have one final category of reaction to cover in this chapter, and this will go pretty quickly. We talked extensively about the electrophilic aromatic substitution reactions, various types of those. What we're going to look at to end this chapter is the opposite, which are the nucleophilic aromatic substitution reactions. And a lot of times you'll see these just abbreviated as NAS. Within the nucleophilic aromatic substitution mechanism, there's kind of two subtypes. We have what's called the addition elimination, which we'll talk about first. Now, before we even get started, I should preface this with the EAS mechanisms, the electrophilic aromatic substitution, are incredibly useful, and you're going to use it all the time. The NAS, on the other hand, are really not that useful. They can be used under specialized circumstances, but they have a lot of weird little requirements to use them. And so they are more, from my perspective, more kind of a mechanistic curiosity than something you're going to use on a practical basis. And in fact, I would advise you not to use these in your synthesis because they tend to lead to more trouble than they're worth. But that said, for some reason, standardized tests love asking about these. So on MCATs, on the ACS final, on other standardized tests, they, for some reason, really like asking about the mechanistic oddities. So that's why we're going to talk about it, so that if you see it on a final, or when you take your MCAT or PCAT or whatever you're going to take, you won't be blindsided by it. So this really is just the mirror opposite of electrophilic aromatic substitution. Okay, so what was observed when people were first kind of playing around with this was that if you had a benzene ring that had a good leaving group on it, but not just a good leaving group, but it also had to have a strong electron withdrawing group, ortho or para to that leaving group. So like that maybe. And you had a strong nucleophile. Say something like that. You could get this to do a substitution. And initially people were not all that perplexed by it because they were like, oh, well, it's just a substitution reaction, maybe an SN2. Could this go through an SN2 mechanism? Well, you've got a strong nucleophile, so that's a good thing. What's the problem with trying to rationalize this with SN2 chemistry?
It's tertiary?
Sort of. More so, it's hybridization, right? When have you ever seen an SN2 mechanism on an sp2 hybrid? Hopefully never, because I don't have it. I mean, think about, there's that, and primarily, especially in the case of a ring like this, there's a geometrical requirement for the SN2 reaction. Right? If you think about it, that requirement was that the nucleophile had to go in and do the backside attack relative to the leaving group. Well, if you're dealing with a flat and planar ring like a benzene, think of what that would mean. Your leaving group is kind of jutting out this direction in space. And so if you were to attempt a backside attack on a flat ring structure, that would mean the nucleophile would have to get inside the ring and pop it out like that, in which case the hydroxyl group would be like in the middle of the ring, which is just kind of absurd. So needless to say, this can't go through SN2 chemistry. Right? No SN2 mechanism because it cannot do a backside attack. How about SN1? So if you remember, the first step of an SN1 mechanism would be the leaving group leaves. The leaving group leaves and leaves you with a carbocation intermediate. Well, that would be kind of weird in and of itself, because you would end up with a benzene cation. But, okay, maybe that does happen. There's something else about this that suggests that it's not an SN1, and that is the requirement of a strong nucleophile. If you remember, SN1 mechanisms happen no matter what kind of nucleophile you have. They happen with water, they happen with methanol, they happen with all of these really weak nucleophiles. These reactions don't happen unless you have a very strong nucleophile. And furthermore, you must have a strong nucleophile, and the rate is dependent or proportional to nucleophile concentration. Which was also not the case for SN1 mechanisms. Right? SN1 was a unimolecular reaction, meaning it was solely the rate was solely dependent upon the concentration of the substrate. Because the rate determining step was the leaving group leaving. So none of this data suggests that this could go through an SN2 mechanism. None of the data suggests it could go through an SN1 mechanism, so something else is going on here. And what was determined was that the first step in this was the nucleophile adding. So the OH minus, the nucleophile is going to go in and attack that carbon where the leaving group is, which is going to cause these electrons to kind of move around. Giving you an intermediate that looks like this. Maybe you can see why now that strong electron withdrawing group is required. And it has to be ortho or para, right? Because if you do the attack like we've just done, the negative charge is going to either end up ortho to the leaving group or para to the leaving group, as I've drawn it here. And so having that strong electron withdrawing group helps to stabilize that negative charge. So here we end up with this negatively charged intermediate that is known as the Meisenheimer complex. And then we just restore the aromaticity and kick out the leaving group. So we're just going to flip these guys back and kick out the leaving group, resulting in an aromatic ring that lost the leaving group and now possesses the strong nucleophile. So what you can see with this, hopefully, is, as I said earlier, these are mirror opposite of the EAS reactions. So for instance, with the EAS, the pi system acted as a nucleophile to attack some electrophile. Here, we have some nucleophile attacking the benzene ring as electrophile. Complete opposite. In the EAS mechanism, we created as an intermediate that positively charged sigma complex. With the NAS mechanisms, we end up with a negatively charged intermediate, the Meisenheimer complex. So they both end up with the same result, meaning substitution of the benzene ring, but through complete opposite processes. Anybody have questions on this? All right, so as I said, these are interesting from a mechanistic point of view. I would not advise trying to use them synthetically because there are a lot of just weird little requirements. Okay. All right, so we looked at the addition-elimination mechanism. Let's go ahead and look at the second class. So the second category was discovered by chemists at Dow Chemical, the big industrial chemistry group. And what they realized was that you could get substitutions of the benzene. Actually, let's do this. Even if you didn't have a strong electron withdrawing group. So they were working with compounds like this, so chlorotoluene type compounds. And what they realized was that if you treated them with a really strong base, something like NaNH2, or NH2 minus is a very, very strong base and also very strong nucleophile. What they realized is that you could get substitution like that. So not too unusual there. The real perplexing thing for them was that that was not the only product. What they also found was that. So two different regioisomers, and these actually did form in 50-50 yield. So clearly this is not going to be useful synthetically because you're making 50-50 mixture of two different things, which presumably means that you would be throwing away half your product. But again, it was interesting from a mechanistic perspective. You know, the fact that this works without a strong electron withdrawing group suggests that this does not go through a negatively charged intermediate. And so through some rather elegant studies, what they were able to show was that the first step of this was actually not the NH2 minus acting as nucleophile. Instead, it was as NH2 minus acting as base. So the NH2 minus would go and grab one of the aromatic protons, and that would force the elimination of the leaving group, almost like in an E2 style mechanism. Electrons come in and kick out the leaving group. Now what is that going to give me? If you follow those arrows, what does that result in? Yeah, it's kind of weird. We've got this benzene compound that now has two double bonds, but the third one is now a triple bond.
Wait, so it doesn't go to the carbon, it goes to between?
Yeah, so it's just like an E2 mechanism. So we're deprotonating adjacent to the leaving group, and then the electrons come in and form a bond. Well, the E2 is normally a double bond with the loss of a leaving group, but we already have a double bond, and so we make the third bond with the loss of the leaving group.
Okay.
So that's going to give us a really weird looking intermediate, something like this. And they call this benzene. It's benzene mechanism. Now it's worth thinking about that for a second. When you have a benzene ring, because all of the atoms are sp2 hybridized, the bond angles in benzene are all 120 degrees. What are the bond angles for an sp hybrid, for a triple bond? Yeah, they're linear, right? They're 180. So this intermediate is highly, highly strained. You've got those triple bonds that would ideally like to have 180-degree bond angles being compressed to 120. So there's a very high degree of ring strain associated with this intermediate, and thus it is very, very reactive. this ring strain can be relieved through the reaction with a nucleophile. And because this is such a highly strained intermediate, it really doesn't matter what kind of nucleophile. You could have the possibility of NH2 minus coming in to attack to relieve the ring strain, or it could even be the conjugate, right? NH2 minus grabbed a proton to give you ammonia, and so even ammonia could come in and attack to relieve the ring strain. It doesn't really matter. You're going to get the same thing regardless. But I'll just do it with NH2 minus because it'll make the mechanism a little easier. But because you've got those two essentially equivalent positions, the two triple bonded carbons, the NH2 minus can relieve the ring strain either through attack here or attack there. And that's why you see that 50-50 product distribution. All right. Any questions on this mechanism? So I do want to show you something, how those chemists at Dow kind of prove the existence of a benzyne, because it's really quite cool. Not that you need to know this or anything, but the way the way they proved the existence of that benzyne was through what's known as a trapping study. So they ran the reaction, but in addition to having the NaNH2, they also they threw in something we've worked a bit with so far, cyclopentadiene. And what that ended up doing was it ended up reacting with the triple bond through Diels-Alder chemistry. So it trapped this highly reactive benzyne intermediate through Diels-Alder chemistry. So if you think about what that would look like, move this down. So the ends of the diene are going to react with the ends of the dienophile. And so it should give us a multi-cyclic structure. They were able to fish that out of them as one of the end products. And that could really only happen through the intermediacy of the benzyne. Okay. Any questions on this? All right, well, that takes us to the end of your Unit 1 material. So you have your exam coming up, I believe it is a week from today. That will occur in here. So you'll have the entire hour, 20 minutes for the exam. And it will cover everything we've talked about from the first day of class up to this point. All right. Any questions on this, the material or scheduling or exam or anything?
So is the stuff that we're going to cover in lab today, is that going to be an exam too?
Yes, so we're going to talk about the directing effects, and that has to do with kind of the electrophilic aromatic substitution. So yeah, that will be covered.
The labs. Thank you.
Yep.
Professor?
Yeah.
So for the homework that's due on Monday, right? The problems are like, I'm having trouble on how to make it meta and ortho and para, or
How to name them?
not name them, but to put like chloro in a meta position.
Oh, For the synthesis?
Yeah.
So the synthesis is, you will have a much easier time with that, after the lab lecture, because that's exactly what we're gonna discuss then. All right, then let me check that real quick. So we're gonna go ahead and get into, we've got about, I don't know, a little bit of time left. So we can go ahead and get into the start of the Unit 2 material, which is pretty good timing. Because we're going to start Unit 2 with mass spectrometry, which is what we were also dealing with in experiment number 3. So, the first thing I'd like for you to notice here is the terminology. Notice it is mass spectrometry, not spectroscopy. So that is on purpose, that is not a typo. The difference here is that when we talk about spectroscopy, what we're referring to is any study of how matter interacts with electromagnetic radiation. And we've already talked about multiple types of that, right? You learned last semester, you talked about infrared spectroscopy that obviously used infrared light. You talked about NMR spectroscopy, which was dealt with the radio frequency waves. You talked this semester about ultraviolet visible spectroscopy, dealing with obviously UV and visible light. Mass spectrometry does not use electromagnetic radiation. Instead, it is based on electrons. Right? And this is actually quite an old technique. Mass spectrometry was originally discovered by someone whose name is probably familiar to you. It was discovered by the British chemist / physicist J.J. Thomson, who coincidentally discovered the electron in about 1898. And so his lab, once he discovered the electron, did a lot of work with electron beams. And so around, I don't know, the early 1900s, he discovered this mass spectrometry technique, and it's been kind of in use ever since. But again, it does not involve electromagnetic radiation. Instead, it uses electron beams. All right. So, the goal of mass spec is, its main goal anyway, is to give you the molecular weight of the compound. It can do a lot of other things as well, but at its most fundamental level, it's going to give you the molecular weight of whatever you're working with. Now, it can also give a lot of other information. It can give you information about how things are branched. Importantly, it can give you information about heteroatom incorporation, which, if you think about, is very valuable and very difficult to get through other means. You know, think about that. If I've got a bromine in my molecule, is NMR going to tell you that? I mean, you might see some de-shielding from the bromine, but lots of atoms cause de-shielding. Are you going to see that in the IR? Think back to your common IR absorptions. Where was the CBR absorption? You probably never learned it, because it occurs way deep in the fingerprint region and gets covered up with all the other junk in the fingerprint region. So it's very difficult oftentimes to know when you have these heteroatoms in your molecule by other spectroscopic means. Mass spec gives you very clear indications of those incorporations. Another distinct advantage of mass spec is you can use very, very small amounts. it doesn't take but nanomolar to even picomolar amounts of substances. Which is pretty crazy to think about. You know, if you think about using the NMR, you're making up an NMR sample. You need, for a good proton NMR, you'll typically be putting in 5 up to even 20 milligrams, depending. That's significant amounts of material, especially when you compare it to nanomolar, picomolar amounts. So mass spec is excellent for doing trace analysis, for the detection of very, very minute amounts of material. And the other thing is that mass spec is ubiquitous in chemical analysis. Anytime no matter what industry you can think of, if you're doing any kind of chemical analysis or unknown analysis, you can bet there's a mass spec around. So used in everything from, again, the FDA, the Department of Agriculture, something like that, is trying to determine the quantity of pesticide on fruits and vegetables. Mass spec is used. Crime labs, in order to identify unknowns, they're going to use mass spec. Even like the Mars rover, you know, I think there's been 3 of them or so now, but the Mars rovers that they send up to the planet and the satellites in space, any type of analysis or any satellites used for chemical analysis is going to use mass spec. Even when you go to the airport, if you've ever gone to the airport and you've been one of the lucky people that they pull aside and they swipe your suitcase, and sometimes if you're really lucky, they'll swipe your hands and they put it in that little machine, that's mass spec. They're looking for explosive residue. Okay? So they're really anywhere any kind of chemical analysis is done, mass spec is around. Okay? The drawback to mass spectrometry is mass spec is a destructive technique. So unlike NMR, you can go prep your NMR sample, drop it in the magnet, take your scans. You can get that sample back. You can dump the NMR tube out into a beaker, evaporate the chloroform, and you've got your sample back. No harm, no foul. That is not the case for mass spec. Because in mass spec, the sample is going to get bombarded by a very high energy beam of electrons, and that effectively blows up the molecules. So once you subject a sample to mass spec analysis, there's no coming back from that. The sample's just gone. It literally gets blown to pieces. So the way I like to envision mass spec, or analogy I like to use, is if you wanted to describe like a glass vase, the usual way you would do it is just walk in the room, turn on the lights, and look at it. Say, well, it's spherical, it's blue in color, describe all the attributes of the vase. Alternatively, you could walk in the room with the lights off, pick up the vase, smash it on the ground, and then turn on the light and start kind of assembling the pieces. That's what mass spec is in molecules. Right? You're going to blow the molecule apart and then look at how it fragments. Look at the pieces that came about. All right? So, as I said earlier, the primary use of mass spec is to get the molecular weight. You can also get a lot of information by looking at the fragments that result, so they can help you determine any kind of branching, types of heteroatoms, as we discussed. But one of the most powerful uses of it is mass spectra are like fingerprints. So no 2 molecules share the same mass spectrum. And as a result, you can create a database of known compounds. And now that we have computational power, the computer can compare a sample's mass spec to the database. And so anymore, this is, you can see where this would be useful in terms of unknown identification. Let's say cops went in and raided a house and found a bunch of random questionable material. The first thing they're gonna do is subject it to mass spec analysis, because they are all connected to databases. The biggest one is from the National Institute of Standards and Technology, the NIST library. But you can run the sample, simply click Find in Library, and it pops up with the identity of the unknown. So it is a really powerful tool for identification of unknowns.
Can you identify like anything or?
Anything that's known.
Like you just throw a rock in there, so you like a rock sphere or something like that, or?
Well, it's usually used for organic molecules. Yeah, so I mean, because as you'll see in just a minute, part of the process of the spectrometry is you have to vaporize the sample. And so if you were to use some sort of an inorganic type material, it's not going to vaporize very well. And so that would be a little bit of a hindrance for that kind of an analysis. Okay, so let's have a look at the instrument itself. So at the beginning, it's very GC-like. And in fact, mass spec is very, very commonly combined with GC. In fact, the analysis that you are doing for experiment 3 is GCMS, gas chromatography mass spectrometry. And so they are very commonly used in tandem. But in any case, the first part of this is you inject your sample, and in this compartment, a couple things happen. Number one, the sample gets vaporized, so it gets turned into a gas. And then you can kind of see this light blue writing. It says the electron beam, and you've got those lines kind of. So what that is it's a very, very high energy beam of electrons. And you can see 6,700 kilojoules. That's a lot of energy. And what the point of that is that it's such high energy that it's capable of ejecting electrons from the molecule. Or said another way, this high energy beam is going to ionize the molecule. And that's important because this tube that the molecules travel through, we call this the flight tube. The flight tube has a strong magnet surrounding it. There's a strong magnetic field. And if you remember your basic physics, if you just had vaporized neutral molecules, they would not be accelerated through the magnetic field. In order for a particle to accelerate in a magnetic field, they have to be charged. So this high energy beam of electrons slams into your molecules. It ejects one or more electrons, which causes the molecule to become an ion.
A positive ion?
Yeah, because they're losing electrons. And then those positively charged ions get accelerated through the flight tube and ultimately will reach a detector. Now, some small portion of the molecules are going to reach the detector as the molecule. Right? If I put in, I think pentane has a molecular weight of 100. If I injected pentane, ionize it, becomes pentane plus, gets accelerated through the flight tube, reaches the detector, I would see peaks at 100 for that entire molecule making it to the detector as an ion. But not many do, because during the flight, most of the ions end up fragmenting. They end up blowing apart. And that's because those, at the beginning, when the high energy beam of electrons hits them, that's a whole lot of kinetic energy that they're hit with. So in addition to ejecting an electron, it causes those molecules to start vibrating violently. and they start vibrating with such energy that they just literally blow apart. And so as these are traveling through the flight tube, they are fragmenting into smaller pieces. And that is what you're going to end up seeing. You're going to end up seeing a spectrum of different sized molecular weight peaks corresponding to different fragments of the original molecule. And so you'll notice this is curved. So only for a given magnetic field strength, only certain masses are going to have the right kind of trajectory to reach the detector. For a given magnetic field strength, if the particles are too heavy, then they won't have enough curvature and they'll hit the outside wall. If they're too light, they're going to get bent too much and hit the inside wall. So at a given field strength, only certain masses can reach the detector. So during the course of the analysis, the field strength is continually changed to select for certain mass peaks. So you can set the range. You know, I want to collect every peak from 0 atomic mass unit to 300 atomic mass unit. And the field strength would adjust accordingly to select for those massed peaks. So in the end, what you end up getting is a spectrum. And that spectrum is going to end up looking something like this. Where you have abundance on the y-axis, and you have what's called the M to Z ratio on the x. Now this sounds a little bit weird. What M to Z is technically the mass to charge ratio of the ion. Now that would be incredibly complicated if we, you know, like I said a minute ago, the first part of this is you vaporize the sample, the high energy beam of electrons hits it, ejects one or more electrons, and so you get all of these different types of ions. So again, that would be very difficult and complicated if you were ending up with all these different charged ions, you know, +1 ion, +2 ion, +3 ion. That would make for a very complicated spectrum. Fortunately, the instrument selects only +1 ions. So while the x-axis is technically a mass to charge ratio, because the charge is always 1, it's really just the mass of the ion. And so what you'll end up with is a series of peaks corresponding to the different masses of the fragments. Okay. Now, this highest mass peak, that is the molecule making it through as an ion unfragmented. That would correspond to the molecular weight of the molecule. And we call this, we usually abbreviate it as the M+, because it's the molecule as a plus charge. And we'll oftentimes call it simply the molecular ion. You might hear it called the parent. Okay. But it's just the weight of the molecule. This highest abundance peak, so the most abundant fragment, and this is what's known as the base peak. And the instrument will automatically call that 100% abundance. And it'll rank all of the other peaks relative to that one. So two important terms, two important peaks to be aware of. You've got the M plus, the molecular ion, which corresponds to the molecular weight of the compound. And then you have the most abundant fragmentation peak. Again, we call it the base peak. All right. Does anybody have questions about kind of the general way this works, or how this technology operates?
What units do they use to like record the mass for that? Just like grams per mole?
Just atomic mass units. Mhm.
Professor, I think I missed it, but what was the importance of the M plus molecular parent?
Oh, it's just, it gives you the molecular weight of the compound. So, which is very useful, you know, if you were working with an unknown, you know, you really don't know what you're dealing with, but subjecting it to mass spec analysis, it would tell you what the molecular weight of the compound was, which is an important piece of the puzzle.
So it's only one peak that tells you that that's considered a parent, or is it?
Yeah, you're only gonna have one parent, or one molecular ion.
And how is that peak decided to be a parent?
It's the highest mass peak. Yeah, because that's gonna be the molecule making it through unfragmented. All the rest of these are some fragment of the original molecule, which is why they're all lower in mass. Now, when we talk about the ionization and fragmentation, you can kind of see it shown here. So you got your molecule, whatever that is, it's a neutral molecule. We're slamming it with this high energy beam of electrons, and that high energy beam of electrons is going to eject an electron. So that's what this is trying to show you here. You're starting with one electron, you ejected one, so you end up with 2 electrons over here, but more importantly, you make that ion of the molecule. And it's not just an ion, right? I mean, it's positively charged because you lost 1 electron. But in addition to that, because it just lost 1 electron, that leaves an unpaired electron. So it's really, if you want to get technical about it, it's not just the cation, it's a radical cation. Because the high energy beam of electron just ejected 1. Giving us both a positive charge and an unpaired electron. Now, when these start to fragment, you know, like I said, you can and do oftentimes get the molecular ion going through the instrument unfragmented. But the majority of these are going to break down along the way. And these fragmentations happen very reliably in basically one way. And I'm gonna abbreviate this as, we'll just do R and R prime maybe. So when you have a fragmentation, actually, let's do it this. Yeah, let's do R. So there's your molecular ion. Right, we've already ejected an electron, which is why it now has a plus dot. It's our radical cation. As this fragments, one piece will always become the plus, and the other piece will always become the radical. So if this guy were to fragment, I could get R plus and R prime dot. One piece always is the cation, the other fragment is always the radical. But these can always occur both ways. So I could have fragmented the way I drew it, with the R plus and the R prime dot, or it could happen the other way as well. R dot and R prime plus. But remember the mechanism of the instrument. We have that magnetic field that the particles are traveling through. So the only ones that are going to be accelerated through the field are the charged particles. So we would only see that and that. Radicals are invisible. Because they don't get accelerated through the magnetic field.
The radicals aren't charged?
Mm-mm. Nope. So the only thing you care about in mass spec are the cationic fragments, because those are the only ones that are observable. They're the only ones that get accelerated through the field. All right, so with all of that in mind, what we're going to do, this is kind of what we already talked about. Yeah, so let me just show you this before we finish today. So this would be a representative mass spectrum. So this is for 2,4-dimethylpentane. What you can see on the slide is that you have that's your highest mass peak. That 100 happens to correspond to that molecular weight. And it's pretty small. Right? It's pretty small because not many of those, once you eject the electron out of this guy, not many of the ions make it through unfragmented. The vast majority of these molecules end up fragmenting in the flight tube, giving you these various different size peaks. Mm-hmm.
The 100 is just a coincidence, right? It doesn't have anything to do with the 100% abundance?
No. That has nothing to do with 100% abundance. The 100% abundance is actually this 41 peak. So that's your base peak. That's your most abundant peak. This
It's just a coincidence.
yeah, it's because that happens to be the molecular weight of this thing. Right? So what do you see? Your molecular ion is here at 100. Your next kind of biggest peak, I guess, would be the 85. So what would that be? So that would be the loss of, my math is right, that'd be a loss of 15. What would the loss of 15 correspond to?
1 methyl?
Yeah, exactly. It is this guy that lost one of the methyl groups. Right? And as you start looking at these, you're going to start to notice patterns. Right? You're going to start recognizing that if you have a 15, it's a methyl group. If you have something that's a 29, that's an ethyl group. If you have something that's a 43, that's a propyl, or more commonly an isopropyl group. A 57, that is a butyl fragment. Okay? So you'll start to kind of get familiar with these fragmentation numbers. All right? So what we're going to do starting on Monday is we're just going to go through some of the more common functional groups and look at how they commonly fragment. Okay? So I think that's probably a good place to stop for today. So I will see you all in about 10 minutes for lab.